Today we shall discuss the very idea of continuity on n-ary topological spaces. As we already know from our earlier presentation, n-ary topologies have been introduced by Seethalakshmi and Kamaraj as an extension of binary topologies of Jyoti and Tangavello. And the idea is that if we have n universes, n sets x1, x2, and so on and so on and so on, xn, and certain family contained in the Cartesian product of power sets, not in the product, not in the power set of Cartesian product, then T is n-ary topology if and only if the following actions are satisfied. Empty set belongs to T, the whole multiverse belongs to T, closure under finite intersections, and closure under arbitrary unions. Of course, intersection and union and complement are defined component-wise. So these are typical topological actions, and as for the members of T, of capital T, they are called the n-ary open sets. This set is called n-ary null, void, or empty set, and we say that A1, A2, and so on and so on and so on, AN is n-ary closed in XT if this set, which has complements of A1, A2, and so on corresponding places, is n-ary open in our topological space. The element like this, where of course x1 belongs to capital X1 and x2 belongs to capital X2 and so on, is called an n-ary point of X, and in general the set of this form is called the n-ary set, where of course, as we can see, A1 is contained in X1, A2 is contained in X2, and so on, and finally AN is contained in Xn. Now we shall consider the very idea of n-ary functions. Consider the following binary space. It consists of two sets, x1 and x2. x1 is here, x2, and we also have certain y1, which consists of three numbers 1 to 3. Assume that A is an n-ary element of X. For example, A may be like this, where this component is contained in x1, of course, and this one is contained in x2. But in general, this is not very important. We just assume that it's an n-ary element, an n-ary set of X. We define the following function, which gets value 1 when point x1, x2 belongs to A, and value 2 when it does not belong to A. Now we see that the inverse image of the singleton of 1 with respect to this function is A. The inverse image of 2, singleton of 2, is complement of A. And the inverse image of 3 is the empty set. And these are all n-ary sets. And moreover, we can conclude that for every subset V of y1, the inverse image under this function is an n-ary element of X. An n-ary element of X. But consider this space. x1 is 1, 2, 3, x2 is 4, 5, 6, and y1 is 0, 1, 2. Now, our function is greatest common divisor of two numbers. One is taken from the universe x1 and one is taken from x2. And now, for example, the inverse image of singleton of 2 consists of these two pairs, 2, 4 and 2, 6, these two binary points. But we may identify this set with the following binary set. As we can see, this set can be considered as binary of n-ary, in this case binary, the set of all n-ary points from the ordered pair A1, A2, such that A1, singleton of 2, is contained in X1, and A2, singleton of A2 is 4, 6, is contained in X2. And something similar is here, in case of singleton of 3. But here, if we consider singleton of 1, of this one here, the situation is different. This set cannot be considered as binary. We cannot identify it with the set of the following form. Note that, for example, we have 2, 5, but we do not have 2, 4 or 2, 6. Yes, 3, 4, 3, 5, but not 3, 6. Hence, okay, there are such domains, such ranges, and such functions that inverse image of V is an n-ary element of X for any V contained in Y1. However, not each F has this property. Hence, according to Seethalakshmi, Kamaraj, and Tangavallu, we may introduce the following definition. A function F from X, where X is our n-ary universe, into Y1, where Y1 is, a single set, is an n-ary function even and only if the inverse image of V is an n-ary element in X for every V contained in Y1, as it's written here. Now we say that the function f from X into Y1 is n-ary continuous if for any V in the topology tau1, which is connected with the set Y1, the inverse image of this set V is in our X topology in T whenever this inverse image is an n-ary element in X. And well, we say that F is T tau1 continuous from X to Y1. For example, every n-ary function is d tau1 continuous if D is discrete n-ary topology. Here we have two other examples. One is the point inclusion n-ary topology, and the second one is A exclusion n-ary topology. There were also other examples of n-ary topologies in our preceding presentation, and moreover, you can look into the bibliography and consider even more different examples. Now there is something interesting. Let us assume that for each j in the index set 1, 2, and so on, n, we have A superscript j equal to this, where A superscript j subscript j is equal to aj, to certain distinguish aj, and on the other places we have our universes xi. This looks artificial, and it's at first glance it seems to be complicated, but later we shall deal with a very simple example. The idea is, and the theorem is, that if we have an n-ary topology on X such that A superscript I belongs to T for every open set, for every A in T, then the projection Pi from X into Xi is Ti continuous from Xt to Xi for each I which belongs to this index set. What does it mean? Well, this can be proved, and we may also say that the condition here, that A superscript I belongs to T for every A in T, cannot be dropped. Consider the following counterexample. We have certain universe x1, x2, and certain binary set A, where A1 is contained in x1 and A2 is contained in x2. And first, our topology is binary empty set, binary universe. Now, A, it's here, and now these are the sets of this form in case of when of course this index set consists only of 1 and 2, A1, x2, and x1, a2. And then the projections on the first, well, component universe and on the second one are binary 2-ary continuous. However, if we consider another topology, which, look here, this condition cannot be dropped. So if we consider another topology which does not contain the sets of this form, then these projections are not binary continuous. For example, inverse image of A1 under such projection P1 is equal to this set. Okay, binary set, but this binary set does not belong to this topology. On the other hand, it belongs to T. So this is a kind of, well, theorem about one of the most elementary theorems about this continuous functions. Moreover, it can be proved that f is t tau1 continuous from x to y1 if and only if the inverse image of each closed set in y1 t1 tau1 is n-ary closed in x t. There are also some other equivalences similar to the corresponding properties from the theory of ordinary topological spaces, and they are all in this initial paper of Tangavellu, Seethalakshmi and Kamaraj. Well, here we shall not deal with so-called irresolute functions, but let us discuss the very foundations of this idea briefly. So, there are universes, multiverses, x, y, and functions such that inverse image of v may not be n-ary in x, even if v is n-ary in y. Okay, just as it was in the case of y equal to y1. And later we shall discuss this topic more thoroughly. However, we may say that function f from x into y, from such multiverse into such multiverse, is named n-ary irresolute if, well, of course, for every v in topology y topology, inverse image of v belongs to, yes, is open in the sense of x topology, whenever this inverse image is n-ary element in x. So this is the idea of n-ary irresoluteness. And this is our bibliography, as I said, papers of these authors who have invented the very idea of n-ary topologies. Thank you very much for your attention.